my pleasure to introduce today's speaker, Dr. Gintner. He is from Slovakia. He received his master degree from Faculty of Mathematics and Physics, Comenius University in Bratislava. Then his PhD received from Carleton University in Opava, in Canada. Dr. Gintner is a particle physicist. He is my colleague. We published a few papers and connected mainly to phenomenology, which is connected to Large Hadron Collider. And today's talk is about Large Hadron Collider. Mickey will focus on round 3. There will be 2 seminars. Today's it's about the machine itself, and tomorrow it's about physics on the LHC. So, Mickey, go ahead.
Okay, thank you. Thank you very much, people, for introduction. And I'd like to thank you, everybody, for the invitation, for possibility to present this seminar, and also I am always happy to come to Opava. Perhaps there is some mysterious connection between my PhD place, Ottawa, and Opava. Sometimes I even once made a mistake on presentation, and I wrote down Ottawa instead of Opava. Anyway, this seminar should be about the beginning of the round 3 of the LHC collider, which you maybe noticed that it started its third run just several days ago on July 5th, which is interesting that it's exactly 10 years plus 1 day after the announcement of the Higgs discovery. This is the must be shown picture of the LHC whenever one talks about the LHC. But it's a nice picture because you can see Alps and Geneva region, and always it's a duty to point out that this is the airport, and the circle depicts the position of the LHC, which is of course dug into the ground some 50 to 150 meters. There are 4 important places where the experiments reside. This is the Atlas experiment, LHCb experiment, CMS experiment, and ALICE experiments. And there is some infrastructures. This is major campus of the LHC and of the CERN itself. Okay, the structure of the Large Hadron Collider is a little bit more complicated. Actually, it also depicts a history of development of CERN as the place where always some new and the largest accelerator in the world was built. So there was time when this proton synchrotron accelerator was the largest in the world, and later this SPS accelerator was largest in the world. And these days, this accelerator structure serves as pre-accelerators of protons, which are fed into the LHC, which is the largest circle in the picture. Circumference of the LHC is about 27 kilometers. As I mentioned, the depth below the ground is between 50 and 150 or 75 meters. The tunnel, which you can see here, is 3.8 meter wide. And the LHC collider, which is a shortcut for Large Hadron Collider, it exhibits proton-proton collisions. So in this, sorry, I have to get used to it. In this tube, there are two beam lines, two separated beam lines, in which two counter-running proton beams are accelerated. And as I mentioned, there are 4 collision points. Again, Atlas, LHCb, CMS, and Alice. Okay, some LHC trivia, which also is like audience is expected to say, wow, what interesting numbers. So tunnel construction was quite long ago, because in the same tunnel there was a large electron-positron collider running operating for in 90s, and then after this collider finished, the same tunnel was used to build LHC. So LHC is running since 2008 till today. The cost of the building the collider was 4.6 billion Swiss francs, and these 4 major experiments cost 1.2 billion Swiss francs. Power consumption of the CERN during LHC operator is 200 megawatts, which is, I read somewhere, that's about 1/2 or 1/3 of the power consumption of the whole Geneva region. From this, LHC and experiments are taking 120 megawatts. And because of these reasons, during winter, LHC is not running, because then the cost of electricity is higher than. So always December and January and February, there is no activity on the LHC. Data produced during collisions. LHC produces some 140 terabytes a day. Plus, if you add the related simulations, then you get 15 petabytes per year. For this reason, there was built the worldwide infrastructure, so-called grid, which is some distributed computing architecture throughout, I don't know, almost 100 countries, where the data are moved immediately to these centers, and you can run analysis even not knowing on which continent actually this analysis is performed. I mean, which computer is taking care of it. Okay, the brief history. The first beam circulation was announced on September 10th of 2008, but it lasted only for 9 days before accident happened. There was because the very strong magnetic fields that are there requires superconductive coils, and there was some material fault which resulted in breaking superconductive state. Immediate heating followed, which boiled the helium and built a big pressure, and it blowed. And the whole structure in one place was blown, and therefore it took another year to repair the place. So I don't know how costly it was, but the actual run started then in 2009, and that was a run 1, which lasted to 2013. Due to the accident, some additional sensors were introduced into the LHC to prevent repeating this situation, this accident, and also greater caution is taken in increasing the energy of the collisions. LHC was projected for 14 TeV collisions, but it still was not reached to this day, and this is probably part of the reason that they are very cautious in taking increases in the energy of the collisions. The most important thing that happened during the run 1 was the Higgs discovery, which was announced. The Higgs discovery was announced 10 years ago on July 4th. As I mentioned, it was exactly 10 years before the run 3 started. And after the run 1, there was so-called long shutdown, which lasted almost 2 years. And during this time was like some parts were replaced, some new hardware was introduced, some repairs were made, and so on. So the accelerator was prepared for so-called run 2, which lasted in years 2015 and 2018. And as you can see, the energy of the collisions were reached almost the projected value. The collisions were taken place at 13 TeV. In 2016, the collision rate increased by 40% against the expected value. In next year, the collision rate even doubled. And in 2018, there was another long shutdown, which lasted to this year. And the whole structure, the collider and experiments, the detectors were updated and upgraded and repaired. And that's where we are now, in run 3, and which July the 5th started the so-called collisions for physics. That means collisions where they actually measure some things, some data which go for, which give physical signal, not only some testing collisions. Okay, why we can ask ourselves, why do we collide particles at all? Why this huge amount of money goes in such specific experiment, and we do it for decades, and basically almost nothing else is heard about in particle physics. So the answer actually can be found a long time ago. Some kind of prototype of all particle colliding experiment, this famous Rutherford alpha scattering apparatus experiment, when he using alpha particles which collided with atoms of gold, enabled to discover the structure of atom, as we all know. And if we use colliding type of experiment, we are doing basically almost the same thing. The reasoning behind is almost the same, except what has changed since that time is that we use much higher energies, much higher intensities of beams, and of course we know much more about the structure. We are reaching into much smaller structures than the structure of the atom. So if we summarize what's going on in particle colliding experiments, what we search for and what we investigate using this approach, then we can say that it's discovering or probing the internal structure of whatever we are colliding. We are probing mutual interactions between these things, and what Rutherford did not have in his experiment, we can also produce new unknown particles that are not known at the given time. So how it all goes? If we want to picture some blueprint of particle colliding experiment, then basically we take particle A, particle B, we collide it, and in the collision, and we look what happened, what's the outcome of the collision, which, for example, might be some 3 particles, as it is in the picture. But how do we know that what happened in the experiment? We have to have some kind of detectors which are capable of detecting these created particles. And if we do not know where those particles go, then we have to surround the interaction point, the colliding point, as much as possible. And of course, the detectors, we are asking that the detectors are able to register those particles. And okay, that might be individual collision, A and B, and we detect some result. But then we have to realize that we are in the quantum physics, and in the quantum physics we rarely have situation when the result is predicted result is unique. More often there is just probability that we find the given final or measure the given final state. And if we repeat the experiment, then we can see different result which can occur in the same as a result of the same initial state, of the same collision. So to get the whole picture, we have to repeat the collision many times again and again, over and over again. So we have to collect sufficient statistics to get the overall picture. And that's what's going on in this collider experiment. That's why we collide so many protons or other particles for such a long time. Basically, we repeat the same experiment again, over and over again, and we are trying to get as much data as possible because of this quantum nature of what we are testing. So, and after we repeat this experiment many and many times, and we obtain, for example, that the angle, how often the particle A is produced at a given angle, the result can be presented as this histogram where here we have the angle of the scattering, and here we have a number of cases, how often it was produced in this or other angle. The experiment would give us, for example, could be presented like these black points, and of course we can have some theories which can be tested against this experiment. It's like these 2 solid lines, 2 different theories, and if we, of course, preferred theory would be that one which coincides with the experimental result. So that's why we need many protons in the collider. So let's have a look on the proton performance in the LHC. The name collider, why there is C in the name in the LHC? Because it's collider, because we are colliding 2 opposite back-to-back protons with the same energy, so we are in the CMS, in the central of mass system. And the injection energy, that means the initial energy of protons that we introduce, that we inject into LHC, is already some 450 GeV. This complex of these smaller accelerators are taking care of the reaching this 450 GeV. And the LHC is doing the rest of the job, so it gets the protons to the final colliding energy. In run 1, it was energies in this range. In run 2, it was increased. I mean, this is energy of a single proton. It was raised to 6.5 TeV, which Lorentz gamma it corresponds to the Lorentz gamma factor almost 7,000. That means some 3 meters per second below the speed of light. And now we are at beginning the run 3. The energy was raised slightly to 6.8 TeV. This is the Lorentz gamma factor, and also we are closer, a little bit closer to the speed of light. This speed means that the period of the time that it takes to run one circle is below 90 microseconds, or in other words, the frequency is larger than 11 kilohertz. And if you are interested where it all begins, where all these protons are taken from, so you can see in this picture this small flask that contains hydrogen gas, and that's where it all begins. It ends in those large, these great collisions in these large hadron collider. So it starts in this small flask, which is stripped of the electrons and then accelerated in this complex to higher and higher energies. Okay, but we are not colliding proton with protons like case by case. Actually, they rather produce beams of protons. The beam, it's like train of almost 3,000 proton bunches. Each bunch contains 100 billion protons, and the size of a single bunch is 30 centimeters in length, and the width is somewhere between millimeters and 16 micrometers. That depends on where we are. If we are in the part that we just accelerate proton beams, that it's millimeters, there it is in millimeters. But if we get to the collision point, there we try to squeeze the beam as much as possible, and there it reaches those 16 micrometers, or now even less. It takes 25 nanoseconds or 7.5 meters between crossing two bunches. So 40 million collisions per second occur. And the energy of the beam, if you sum up the energy of all protons in all bunches, then you get some 360 megajoules, which is equivalent to 77 kilograms of TNT, and this energy would be able to melt 1 ton of copper from room temperature to complete liquid. So it's quite, they have to be careful that, so that the beam doesn't hit the wall of the pipe. Yeah, otherwise it would melt it and made some damage. So, and how they are able to steer the beam so that it doesn't hit the wall, they have some 10,000 superconducting magnets, 96 tons of superfluid helium, and there are dipole magnets and quadrupole magnets. Dipole magnets are used for steering the beam, and quadrupoles are used to squeeze the beam right before the collision. Okay, now, of course, the important quantity we mentioned already several times is the energy of the collision. But the other important parameter, which is related to how many collisions we get per given time, is the luminosity of the beam. Simply speaking, luminosity is basically the number of proton-proton collision per unit time, per unit area. So the higher luminosity means more collisions, higher statistics, more data to analyze. And in long-term run, we are interested in the accumulated amount of data. So we are interested in integrated luminosity. We integrate it over time. And then this number is also interesting parameter. If we then want to know how many events of given type, the proton-proton creating some final state X, we have to multiply this luminosity by the cross-section of the given process. Cross-section is some characteristic of the process, and this simple calculation tells us how many events we produce. So actually, if we look at the luminosity in the previous years, these are numbers in 10 to 33 second per centimeter squared. So you can see that the luminosity increased from year to year. And here you can see the accumulated integrated luminosity. Of course, the reality is such that the beam is run, in good days they run beams for I don't know, 6 to 10 hours. It depends on circumstances, various circumstances like outside temperature or earthquake or big train passing by, and all these circumstances can disturb the stability of the beam. And of course there are some other reasons to interrupt running the beam in the collider. So you can see the footsteps of this development in this graph, how the integrated luminosity increases. Sometimes there are time periods when it's not increasing, other periods when it increases to larger values. And as you can see, as I mentioned, that the winter month, there is nothing, no activity there. Okay, that's the beam, that's the source of collisions. And now the detectors that are measuring or registering the result of those collisions. Those are those 4 major detectors: Atlas, CMS, LHC, B, and Alice. And there are many much smaller experiments which are exploiting the possibility of this whole environment. They would not solely, they would not be a good reason for building LHC, but if the LHC is there and already we have such energies and such collisions, then many people come with smart ideas what else could be measured. So these are some of those small experiments, just by name. And those experiments are, for example, they are looking for magnetic monopoles or dark matter particles, WIMPs. They are studying neutrinos, and so on and so forth. I will not talk anymore about these. I will focus only on in this talk today, I will focus only on these 4 major detectors. One of these, the largest, is the Atlas detector. You can see that it's really a huge beast. Protons are coming from these 2 sides and they collide right in the middle. And all this whole structure is a just astronomical amount of various components, all focused on detecting various properties of the produced particles. The again, the overall layout of any particle detector can be shown in this picture. From the left to the right, you go schematically from the point of collision to the most outer structure. And first, there are so-called inner detectors, which serve to track the path of individual particles. They try to establish actual trajectory. This layer is followed by electromagnetic calorimeter. The electromagnetic calorimeter is the purpose of this detector is to measure the overall energy of photons, electrons, and positrons, and it is projected in such a way that no photons or electrons can get further than to the electromagnetic calorimeter. That means, okay, the third layer is so-called hadronic calorimeter. It serves for measurement of the energy of neutrons, protons, and pions. And again, it's projected in such a way that none of these particles make it further than to the hadronic calorimeter. And finally, the most outer layer is a muon detector, because muons are they are 200 times heavier than the electrons, so their ability to go through all these layers is very, very big. And basically, they are not even stopped in the last layer. They are only registered there. If you see that you have some track in the most inner detector, and also you can see that the same thing made signal in the muon detector, then you say, okay, it was a muon. So what we are actually able to detect, photons, you see no track in this tracker, and you can see energy in electromagnetic calorimeter, then your conclusion is that you saw photon. If you see energy in the electromagnetic calorimeter, and also you can see the track in the tracker, then you conclude that these are electrons or positrons. If you see the signal that goes through all these layers, then those are muons. Pions and protons, they leave the trace in the inner detector. They could leave some energy in electromagnetic calorimeter and the rest of the energy in the hadronic calorimeter. Neutrons, because they do not have electric charge. Oh, I forgot to mention that, but probably you already deduced it, that inner detector, this tracker, is sensitive only to electrically charged particles. So neutrons do not leave any traces in the first two layers, but they deposit the whole energy in the hadronic calorimeter. And then there are neutrinos produced, but they interact so weakly that they do not leave any trace in any of these detectors. So this is how each particle detector can approach these components they have at their disposal to try to identify whatever was created in the collision. So if we return back to the Atlas detector, then the software that tries to depict and to visualize everything that was detected in the collision looks somehow like this. And this is the side view. That means the proton beams are approaching from left and right hand side. And this is the cross-sectional view. And again, these different colors suggest those different layers. So this would indicate the tracker detector. Again, tracker detector is this part. Then this color indicates the electromagnetic calorimeter. This is the hadronic calorimeter, and these are the muon detectors. So, and these, you can see that you can see the actual tracks in the tracker detector, which are followed by these yellow colored boxes, which indicate how much energy was deposited in the electromagnetic calorimeter, and then the same thing in the hadronic calorimeter. And here you have clearly you have muons, because they made a signal also in the most outer layer. But you probably realized at this point that this is a very limited amount of particles that we are able to detect. If there are some particles that do not interact or interact extremely weakly with the material of the detector or with this structure, then we do not detect them. Neutrinos was one example. Other problem could happen if the particles created in the collision have too short lifetime. They simply can decay so quickly that they do not reach the detector. Also, in the collisions, there could be created bound states of particles. So those particles are hidden inside of some structures which the detector is not able to distinguish, for example, quarks in hadrons. And also, the last reason for not detecting every particle is that each detector has some dead time when it detected something, and it takes some time to reset itself. So, and if that time goes something through it, it's not detected. And also the whole things, the active parts of the detector must be somehow built into some supporting structure where there are no detectors. And therefore, if particle goes through this supportive structure, we cannot see it. And one major blind area is area around the beam pipes, which just are where the protons are getting into the collision point. So let's look what particle physicists are doing about these problems. So let's take the first reason, none or extremely weak interaction with detector. Example was the neutrinos, or there could be other weakly interacting new particles like graviton, WIMPs. And the only possibility that we have how to solve these missing particles, not detected particles, is to rely on the conservation laws. So we know what kind of energy and what kind of total momentum we are investing into the collision. And then if we are able to measure the outcome energy and outcome momentum, we can compare these two, and we can say, okay, something is missing. From the momentum, we can even say which way it went, what is missing. And that's a principle, general principle, how to approach it, which doesn't work to its full in the case of proton collisions. Proton collisions are a little bit unfortunate because protons are not elementary particles. So we know that we are investing, let's say, 13 TeV in the collision, that's the total energy. But this energy is distributed among the particles that the protons are made of. And each substructure carries just some part of the energy, some part of the momentum. And the actual collision occurs not between protons, but between these constituents of the proton. So we do not know what energy actually was in the beginning of the given collision. We can say it's not more than the total energy. And also we don't know what's the initial momentum. Actually, we can say something about it. If this collision is very energetic, so highly relativistic, then we can say that the movement of constituents in the perpendicular direction is negligible. So at least we can say that in the plane perpendicular to the collision axis, the initial momentum was 0. So we can, that's so-called not perpendicular, transverse, sorry, thank you. Transverse momentum. So we can use transverse momentum to analyze missing particles in the case of protons. So that's, we have limited possibilities. It's much easier if we collide electron and positron, for example, which do not have any structure, and we have everything under control. Lifetime, okay, the second reason why we do not see the particle that is produced, the lifetime is too short. Such example is, for example, W plus minus or Z0 bosons, electroweak carriers of electroweak force. Their lifetime is about 10 to the minus 25 seconds. So if you quickly calculate, if you multiply this with the speed of light, and okay, let's not argue about time dilatation, then we get the mean decay path, something like 10 to the minus 16 meters. That's it decays even within the nucleus or within the size of the proton. So there is no chance to build detector that would be able to see W and Z boson directly. But how can we learn that such particles exist? There is something I call Nobel Prize trick, because this was used for discovering many of such particles, and which was followed by getting the Nobel Prize for it. Simply, if we analyze the structure of the amplitude to get such result, then the amplitude, if there is a X particle that decays to A and B, and in the second case there is no such particle, in this case that the X particle exists, there is a peak in the spectrum right at the invariant mass of the decay products of the X particle. So if we observe such a peak in the invariant mass distribution, then it's a candidate for arguing that there is some underlying short-lived particle that produced this A and B. How to detect undetectable? Third case, the bound states, quarks, which quarks theory tells us that quarks cannot be produced as a free particles, and experiment confirms that we were not able to produce free quarks, even though we tried for decades. So it seems that we already agree that it's not possible. And the reason is very strong force between these quarks. And if we produce quark-anti-quark pair in such collision, these quarks are carriers of the whole energy of the collisions, and they are trying to separate. But as they try to separate, they hit the limit of some energy advantage, and it's easier for them to produce more and more quarks, to invest this energy to producing more and more quarks, which are then bound to other quarks, and at the end, very quickly at the end we have a bunch of hadrons. Before it reaches any detectors, there is just a bunch of hadrons, which are carrying traces of the original momentum and energy of those mother quarks that produce these hadronization states. In the detector we can see, like we call it jets, we can see many particles that are somehow collimated into the same direction, and if we calculate overall energy and overall momentum of these jets, we deduce that, okay, that was the momentum and energy of those parenting quarks. And okay, so it's possible that some new structures we are not aware of also contain some bound states. So this would be used. This would be something that would be, if this is observed in the experiment, then we can think this way about the mother particles. And the fourth case is when there is when particle hits the dead time of the detector or goes through the blind spot. Okay, I discussed already why, where. So how we solve this? We are approaching this from the point of view of some software simulations. We simply, based on our theory, we try to predict what should go into those blind spots, and we compare. Then we import these blind spots into our simulation, and we compare whatever is the result with the reality. We can then adjust some parameters so that the experiment fits the theory, the simulation, and then we can predict through the simulation what kind of particles were probably produced statistically into those areas that are not sensitive enough. Okay, so this is some overall philosophy about the LHC and collider as such and detecting of particles. So let's have a look at the run 3. As I already mentioned, the energy of the collisions was increased from 13 TeV to 13.6 TeV, which is again a world record for the collision energies of protons or any other particles. We are working with more intense beams than in run 2, increased by 50%. The collision rate was increased by 50%. They introduced some new techniques how to increase this luminosity through so-called luminosity leveling. So they are actively adjusting the crossing angle, because I mentioned that we have back-to-back colliding protons that are approaching in one line, but it's not completely true. They are crossing each other at some angle, very small, for some reasons that would be very technical. But playing with this parameter, they optimize the luminosity, and they play as the beam runs for hours. Then it's different angles and different squeezings are optimal for getting the most from those collisions. So up to in previous runs they have these things were fixed and they went as they were set up in the beginning, but now they actively are entering the parameters and they play with it and optimize it. And also they, using this technique, they manage to increase how long they are able to run one single beam. Now they are able to run it for 10 to 15 hours. So it's about doubled the time. Because after they deplete, sort of, or better to say, the parameters of the beam decay as it runs for hours in the collider, then they dump the beam, so the collider is empty and they have to inject new beam, and again, usually the next day, and they run it for several hours, so this time was increased, which will increase the integrated luminosity and it will increase the number of the statistics. They say they would achieve more data than run 1 and run 2 together. And the major reason for this run 3 is still the same as for run 2 and run 1. Study the Higgs boson properties after it was already discovered. I will talk tomorrow about what kind of properties and why we have to continue with this. And the second major goal is the search for physics beyond the standard model. Again, I will talk about it tomorrow. Now I will go through those 4 major experiments. I will tell the most important improvements for run 3. So let's start with ATLAS, this acronym for a toroidal LHC apparatus. That's as I mentioned, that's the largest of the experiments, of the 4 experiments. Even they say it's largest, well, we know it's the largest particle collider detector ever built. One of 2 Higgs boson co-discoverer in those 2012. They announced the discovery of Higgs boson along with CMS detector. And the major renovations concern the replacement of these 2 parts, these muon detectors at the ends of the detector. You can see in this picture this new small wheel. Then they completely updated trigger system, the most inner part, and also they heavily changed the software which processes the data, reconstructs the events and performs the analysis. The CMS is another general purpose experiment. The ATLAS was the largest detector. This is the heaviest detector, more compact. That's reflected in the name, compact muon solenoid experiment. This detector is specialized for search for rare phenomena in beyond the standard model physics. And what they renovated, the so-called pixel tracker, that's the smallest part of the tracker layer. We are talking about distinguishment at the level of millimeters or even micrometers in determining the path of particle. They upgraded the so-called Brill detector. That's the detector that actually measures actual intensity of the beam, because this intensity to have the proper parameters of the beam, it's important in evaluating of whatever you see in the final state of the collision. Then there is something, they added so-called gas electron multiplier, which improves the detection of muons close to beam pipe. And they have completely new software for data filtering and processing. LHCb detector is the 3rd one, and it's very interesting detector because the first 2 were sort of symmetrically built around the interaction point, and this detector have the interaction point right here, and it's all specialized in detecting what goes out of the collision in a very small angle around the beam. Its purpose is to study composite particles that contain B quarks and look for deviation from the standard model. They say this is the most upgraded of the 4 detectors. For example, for the tracking area, they added some 10,000 kilometers of optical fiber. It's completely new. That serves to establish tracks of photons, I think. Then there is an important vertex locator, because as they look at the hadrons that contain B quarks, many of those hadrons are very quickly decaying, but not as quickly as those Z and W bosons. The primary and secondary vertex are usually typically millimeters or centimeters apart of each other, so they are able to distinguish it, but they specialized in these things. And completely new data acquisition system. And the ELIS detector, okay, now you can see that I cheated a little bit when I said the LHC is proton-proton collider, because 1 month each year it runs heavy, relativistic heavy ions, particularly lead-lead ion collisions, where they are searching, or they found already, so-called quark gluon plasma, very early, which is hypothesized that it was present in the universe very early after the Big Bang, and it's present in some perhaps in some exotic stars and so on. So this detector is specializing in those collisions, and major upgrades are already prepared for the stage of LHC, which will probably come after the run 3. I will tell you what it is. And in run 3, they also try to observe proton oxygen and oxygen-oxygen collisions. And the reason for that is they are trying to study what happens when cosmic rays hit the upper levels of atmosphere, especially those that have energy above 10 to the 16th electron volts. Okay, and now what happens, what will happen, what they have in plan, what kind of plan they have for after the run 3 is finished. Run 3 should be finished either in 2025 or 2026. Then, as you can predict, there will be long shutdown number 3. And they expect that in 2029, after this shutdown, which they use for, again, another upgrade of the LHC, they turn it into so-called high luminosity LHC. That means the luminosity of the beam will be up in one order, producing some 50 million Higgs boson per year. They perhaps achieve the final planned energy 14 TeV, and and I said it should be operational in 2029. Let's hope we will be around and see what it brings. Okay, so that's all for my today's talk, and tomorrow, if you come, despite this weather, then there is another seminar which is continuation of this one, and I will talk about the main research goals of the LHC for this run 3. What is the reason for running this LHC again for several years and invest all the money? Okay, thank you very much.